Okay. Hello to one and all present here. Myself Kalpita Nath, and I am the TA of the Transport Phenomena course online problem solving class. And this is the sixth week of the online problem solving session of Transport Phenomena. Myself Kalpita Nath, and I am Prima Physics Scholar of IT Kharagpur. And this course has been carried out under the guidance of Professor Sunando Dasgupta from IT Kharagpur. Without further ado, we'll go on with the week 6 of this problem solving class of transport phenomena. And for the week 6, we'll start up with the first problem that is from previous week, that remained unsolved previous day. I'll give you 5 minutes to think about this problem and to try and solve it, and after that we'll start with the corresponding solution. That previous day was left undone. Okay, so let's proceed with the solution. Okay, I'll give you 5 minutes, and after that we'll start with the solution. Okay, so we should now start with the solution for the previous day problem. That is the class 5 problem. So I'll share the screen with you all. Okay. So what is the question? Is that water flows at velocity of 1 meter per second past a flat plate with L is 1 meter in the flow direction. Okay, that's the length is flow meter of the flat plate. Boundary layer is stripped so that it becomes turbulent at the leading edge. Okay, so it is turbulent flow. Evaluate the disturbance thickness, the displacement thickness, and the wall shear stress at x is equal to L. Compare with laminar flow, and that is maintained at the same position. So first we have to find everything for that is the displacement thickness, disturbance thickness, and the wall shear stress for turbulent flow, and same way we have to find for the laminar flow. Okay, and then what we have to do, we have to compare both of them, and it is said to be assumed like to assume 1/7 power turbulent velocity profile. Okay. I hope I am audible and visible to you. So, we'll just start with the problem solving. First is class 5, problem 13. Okay. So, first, flat plate boundary layer flow is given, and 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 turbulent flow from the leading edge is given, and we need to assume 1/7 velocity profile. Okay. First, we need to find displacement thickness, then we need to find disturbance thickness, then we need to find shear stress. Okay, and then the comparison with laminar profile. Okay, first applying the results from the momentum integral equation. From momentum integral equation, we have to apply results from that. For first, for turbulent first we have to find everything for turbulent profile. Okay, so for turbulent flow, governing equations are delta by x is equal to 0.32 by Reynolds number 1/5.
delta star is equal to 0 to infinity 1 minus small u by capital U dx dy, and Cf is equal to tau w half rho u square, that is 0.0594 by Reynolds number 1 by 5. For turbulent flow, this is the equation for skin friction coefficient. At x is equal to L with mu is equal to 1 into 10 to the power 6 meter square per second for what T is equal to 20 degrees Celsius. Reynolds number is equal to UL by mu is equal to 1 meter per second into 1 meter into second by 10 to the power 6 meters is equal to 10 to the power 6. This is the answer. Now 10 to the power 6 is greater than 5 into 10 to the power 5, so the flow is turbulent. Okay, so Reynolds number, not Reynolds number. Now we have to find delta L. Delta L is equal to 0.382 by Reynolds number 1 by 5 L. 0.382 by 10 to the power 6 by 1 by 5. Okay, this is into 1 meter is equal to 0.0241 meter. That is delta L is equal to 24.1 millimeter. Okay. Now we have to find displacement thickness. So small u by capital U, first we need to find, that is y by delta to the power 1 by 7. It's given following 1/7 power. So therefore delta L star is equal to 0 to infinity 1 minus small u by capital U dy. Delta L 0 to infinity 1 minus small u by capital U dy by delta. Delta L is this one. Delta L 0 to delta 1 minus small u by capital U delta y by delta. Now when eta is equal to y by delta, when y is equal to 0, eta is equal to 0, y is equal to delta, eta is equal to 1. So therefore delta L star will be is equal to delta L 0 to 1 minus small u by capital U 1 minus small u by capital U d eta. Delta L 0 to 1 minus eta to the power 1 by 7 d eta as small u by capital U as small u by capital U is equal to eta to the power 1 by 7. Therefore delta L star is equal to delta L eta minus eta to the power 1 by 7 plus 1 by 1 by 7 plus 1 0 to 1 is equal to delta L eta minus eta minus eta to the power 8 by 7 by 8 by 7 0 to 1 delta L 1 minus 7 by 8 is equal to delta L by 8. Therefore delta L star is equal to 24.1 by 8, that is 3.0125. Next is skin friction coefficient. From there we can get shear stress. 0.0594 Reynolds number to the power 1 by 5. That is 0. That is 0.0594 by 10 to the power 6 1 by 5. 0.00375. From here tau w we can get CF half rho u squared. 0.00375 into 1 by 2 into okay, 1 by 2 into 999 kg per meter cube, 1 square meter square per second square into Newton second per kg meter. So tau w is equal to 1.87 Newton per meter square. Okay, this we have derived everything for turbulent flow. Now we'll come to laminar flow. Laminar flow. For laminar flow, delta L is equal to 5.0 root over Reynolds number 5.0 by 10 to the power 6 of 1 meter. Delta is equal to 0.005 meter or 5 mm. Okay. For laminar flow, small u by capital U is equal to 2 eta minus eta square. This we already have derived, and today we'll derive it again. I'll show you how. In the there are some later question where I'll show you the derivations. 0 to infinity 1 minus small u by capital U dy is equal to 0 to delta 1 minus small u by capital U dy. From Laplacious solution, eta is equal to y root over u by nu x. Eta nu x by u. Y is equal to eta nu x by u. Or dy is equal to d eta root over nu x by u. Therefore, delta star is equal to 0 to eta maximum small u by capital U root over nu x by u d eta. This because eta will be maximum. It is the ending of boundary layer, that is eta is 1 at y is equal to. That's why that is the maximum eta. So it can be written as eta max. So okay, now root over nu x by u 0 to eta maximum 1 minus small u by capital U d eta. Corresponding to upper limit on y, that is y tends to infinity, eta max tends to infinity, or eta max is equal to 5. How it is given in question. Okay, so it is given in question that we can see the graph first. We can see the graph that eta is at, okay, we can see here Okay. Eta is equal to 5. That is eta max is equal to 5. Eta max is equal to 5. Oh, eta here is y root over u by nu x. So if we put the value of everything uh, and then we calculate everything is given in the question, we'll find eta max to be 5 maximum. Just put the values of others. So therefore we need to find delta now. Delta is 5.0 x by root over Reynolds number, that is already known for laminar flow. 5.0 root over u x by nu x is equal to 5.0 by root over u by nu x, or root over nu x by u is equal to delta by 5. Delta star is equal to delta by 5 0 to delta, this we found, delta by 5 0 to 5 1 minus small u by capital U d eta. Now small u is equal to del psi by del y, and v is equal to minus del psi by del x, where psi is the string function. Okay, now what we'll do, for incompressible flow with zero pressure gradient, del u del x plus del v del y is equal to 0. This is equation 1. And u del x plus v del u del y plus v del square u del y square. Now eta is equal to y root over u by nu x. This is equation 3. Now for Blasius equation, delta is directly proportional to nu x by u. So y by delta is directly proportional to y by root over nu x by u. So therefore eta is equal to y root over u by nu x. From here we found out eta is equal to y root over nu x. Okay. So now we have to find this we have to evaluate this. So we'll define a dimensionless stream function, that is f eta is equal to psi by root over nu x. This is equation 4. In equation of u, small u is equal to del psi del y is equal to del psi del eta del eta del y. By equation 4, 4 is equal to 4 is equal to del psi del y is equal to del psi del eta del psi del psi del eta. Function of del psi del eta. Psi is equal to, means here it is root over nu x u df d eta. Okay. Then by equation 3, del eta del y is equal to, by equation 3, root over u by mu x. Therefore small u is equal to del f del eta root over u by nu x into root over nu x here. So small u came out to be u df d. Now in equation A, delta star equation is equation A. In equation A, if we put delta star is equal to delta by 5, 0 to 5. What is equation A? Equation A is delta 5, 0 to 5, 1 minus small u by capital U d. So this came out to be delta by 5, 0 to 5, 1 minus df d eta d eta. This is equal to delta by 5 eta minus function of eta 0 to 5. Okay, that is S. This will be into 3.283. 3.283. Therefore, delta star is equal to delta by 5, 5 minus 3.283. And this delta is 5. Delta cannot be 5. Maximum delta is 5. So delta star is 1.716. Now, skin friction coefficient 0.664 by root over 0.664 by root over 10 power 6. Therefore, tau w is equal to Cf half rho u square and 0.664 by root over 10 power 6 half into 999 kg per meter cube into 1 square meter square by second square into Newton second kg meter. 0.332 Newton per meter square. This is tau. Now comparing laminar and turbulent at x is equal to f. Disturbance thickness, that is delta turbulent by delta laminar. This is disturbance thickness 24.1 mm and 5.00 mm is equal to 4.8. Displacement thickness delta star turbulent by delta star laminar 3.0125 by mm by 1.7167 1.755 mm. So the wall shear stress tau w turbulent and tau w laminar 1.87 by 0.332 Newton per meter square Newton per meter square is equal to 5.63. So these are the answers. Okay. we need to find out this first. Next is class 6, question number 1. Let us first change to question number 1 of today's class. During the flight, aircraft mostly experiences friction drag. Yeah, state that which it is true or false. So pressure drag is comparatively smaller due to the shape of the aircraft, as we can see in the diagram itself. The air flowing past an object pushes harder against the front than at the back. This difference was create a pressure drag. As the aircraft speed increases, the drag on the aircraft generally increases much faster. Doubling the speed makes the airplane encounter twice as much air moving than earlier and causing drag to quadruple. The air pressure against the leading side of an object is higher as compared to the pressure is higher than the pressure at the backside, and thus there is lower pressure at the backside because of the randomly churning eddies at the other side of the streamline, at the other side of it. Streamlining reduces the if we create a streamline, it reduces the pressure drag. Okay, so how? Like, let me show you with few diagrams. Like, if there is a plank and if there is a disc, suppose disc, and stream is coming from here, it will be like this. It will be like this, and there will be large turbulent wake for disc. Then, if there is a sphere, there will be a little smaller eddies. And if there is a teardrop shape, as we can see in airplane, it will be like this. And this is the smallest wake. Okay. But at the same time, keep in mind that streamlining also increases the friction drag. Thus, the more you streamline an object, more elongating its rear surface will be, and the more you reduce size of the wake, the more you reduce the size of its wake, the more is you reduce the size of the wake, and the resulting pressure drag. But elongating an object increases its surface area and increases the effect of friction. That is the another form of drag. It will increase the friction drag and it will decrease the pressure drag. Thus, an object must be tapered enough to reduce the size of the wake, but it must also be short enough so that the accompanying friction drag doesn't offset to lower the pressure drag. Okay. As friction drag is also less, the pressure drag is also less. So we need to minimize the area. Okay. So let us proceed to second question now. Water flows over a flat plate at a speed of 1 meter per second, and the plate is 4 meter long and 1 meter wide. The boundary layer on each surface of the plate is laminar. As the velocity profile must be maybe approximated as linear, given nu and density of water, and determine the drag coefficient and mark the correct answer among the following. Okay. So this is a rather simple question. We have solved many this kind of question earlier. So I'll give you 2 minutes for this and then we'll start with the solution. Let us proceed with the solution of this. Velocity is given as 1 meter per second and length is given of the plate as 0.4 meter and width is given as 1 meter and boundary layer is given as laminar. Okay, so drag coefficient we need to find later, and first we need to find drag force, right? So half rho u square, so therefore drag force is cd half rho u square into 2, as there are two surfaces, it's already said in the question. Reynolds number is lu rho by mu, that is lu by mu, that is 0.4 into 1 by 8.9 into 10 to the power minus. So that is 449.435 into 10 to the power. The flow is laminar. Now, for laminar flow flat plate, CDL is equal to 1.328 by Reynolds number 0.5. This we already know for laminar flow. So CDL is equal to 1.328 by 449.43 to the power 0.5. 0.6264. Acha. First we have to find the drag coefficient for laminar. So the drag coefficient for laminar flow is 0.6. This is option A. Next question is determine the drag force. The drag force is 0.6264 into half into 1000 into 1 square root. So this come out to be 62.64 Newton. This is option B, right? Now we'll proceed to question number 4. The lift force on an aerofoil with lift coefficient CL in a fluid with density rho and velocity u is given by which one of the following? I'll give you 2 minutes for this. You will mark the answer and then you will get back to me. Okay. Okay, so let us start with the solution of question number 4. So for question number 4, let us consider a leaf force that is acting on an airfoil is found experimentally through the wind tunnel, and it comes out to be half CL rho V infinity square. That is C. But we will derive for an element 2 the drag force and the leaf force. Suppose this is a fluid, this is a solid element. This is solid, and this is the pressure that is acting. This made angle theta with the horizontal, and this is tau w d. This is p d a cos, and this is tau w d a cos 90 minus theta. This is direction of force. Now PDA cos theta pressure applied in direction of flow. So the lift force is 0 to A dFL is equal to FL is equal to 0 to A tau W sine 90 degree minus theta. This length, this length minus as pressure will be this is going out and pressure will be going in. So this will minus out minus in P D A sine theta D. The surface is parallel to the direction of flow. The surface is parallel to the direction of the flow 0 to A tau W cos theta dA minus 0 to A P dA sine theta. 0 to A P d minus P. Now the surface is if the surface is perpendicular. This was if the surface is parallel. The surface is perpendicular. Net force is 0 to A tau W cos 90 degree dA minus 0 to A P dA sine 90 degree minus 0 to A P dA perpendicular. Sorry. This is cos theta. Cos theta. Sorry. This will be 0 degree. This is 0 degree. As here the plate, this is the plate, this is the PDA, this is 90 degree, this is. So angle of PDA with horizontal is PDA with vertical. Angle of PDA with vertical PDA with horizontal is 0 degree. ঠিক আছে? So this is 0 degree and this is 0 degree. So this is 0 to A tau WDA equal to tau. This is for the previous case. For this case, when the flow is perpendicular, when it is perpendicular to the direction, surface is perpendicular to the direction of the flow. This is flow direction and surface is perpendicular, so theta is 0 for this case. Now question number 5. Let us go to question number 5. The lift force, which one mode of air transfer requires no medium to energy transport? Obviously this is radiation. This is 5 is. Now 6. Heat is getting transferred from chain to of static molecules from hot area to an object to a cold area. Choose the correct mode of heat transfer. This is conduction. Now question number 7. Heat transfer conduction in regular motion to which of the following? Thermal potential difference upon thermal resistance. That is given. Now question number 8. The cricket bowler bowls can use the seam of the ball to create or choose like to create which are the following: turbulent on both sides of the ball, or laminar on both sides of the ball, or laminar on one side of the ball, turbulent on either side of the ball, and now answer me this. You take 2 minutes for this because this requires some critical thinking to be done, and after that we'll go on with the solution. Okay, okay, let's proceed now. We have got enough time to think about it. Now I'll show you, and I'll rather explain you some very interesting. I hope Sir has already taught some.
I'll just clarify you everything else. So as the ball is flying through the thin air, a thin layer of air that is called boundary layer forms along the ball surface. The boundary layer cannot stay attached to the ball surface all the way around to the ball, and thus it leaves or separate from the surface at some point of time. Like if here the ball is, boundary layer is here, it will separate at some time, after some time, like this. So, not like this. Let me redraw it. Like if the ball is like this, it will get separated. It will get separated and waves will be formed here. Waves. Okay, this is called boundary layer separation. The location of this separation point determines the pressure, and a thin and if a relatively late separation results in lower pressure on that side. A side force or swing will only be generated if there is a pressure difference between a swing will be generated in the ball, like if there is a difference in pressure between both sides, then a swing will generated, like ball will move like this or will move like this, right? And we'll throw it, it will move either like this, in swing or out swing. Okay, now the boundary layer have two states, and a laminar smooth state or steady state, that is laminar, and a time varying chaotic turbulent state. Okay, so now the transition from the laminar to turbulent state occurs at a critical speed that is determined by the roughness of the surface of the ball. The rougher the surface, the lower is the critical speed. That is easily the turbulent flow will be achieved. That is, if the ball becomes older, the roughness of the surface will increase, where we won't touch the surface. There will be two sides, I'll show you later, like I'll explain it to you later. So when the roughness increases, the speed of the critical speed when the flow will take transition from laminar to turbulent, that will also decrease. However, on a very smooth surface and at a nominal speed, a laminar boundary layer can be forced to turn turbulent by tripping it with a disturbance. Okay, at nominal speed. The disturbance can be in the form of local perturbance or surface roughness, which adds turbulent eddies to the laminar flow to become turbulent. As I've already said, if there will be rough surface, local eddies will be developed and the flow will become turbulent. It is similar to putting a finger into a smooth stream of water from tap. When you open the tap, you will place the your finger in between. The water will flow like this. So there will be eddies generated here, and the pressure will be low here. How small the chaotic turbulent motion is generated downstream of the finger location. However, it turns out the turbulent boundary layer, because of its increased activity and energy, can stay attached to the ball surface to a longer distance compared to a laminar layer. Turbulent layer can attach to a longer distance as compared to laminar layer. At high speed, for in case of ball at high speed, if we throw the ball at high speed, the flow will be laminar on both sides, turbulent on both sides. At moderate speed, it will be laminar on one and turbulent on other, due to the presence of the seam in the proper orientation at an angle to the flow direction. The flow can be laminar on one and turbulent on the other. I'll show you how. At low speed, the seam will have no effect at all. Okay, so now type of throwing. Type 1 is the conventional bowling. Now for new balls, what is happening? This is the vertical. Okay. This is the ball and this is the seam of the ball. It is at an angle to this vertical line. This is at an angle. The seam is at an angle to the vertical line. Okay. So here there is no disturbance in the flow. So it will be laminar flow. And here, as because of the seam, the seam will disturb the flow and there will be turbulent flow. So this side is turbulent, this side is laminar, and hence this is low pressure region. Turbulent is low pressure and laminar is high pressure. So the pressure on the turbulent side is less as compared to the laminar side. So if the seam angle is like this to the that is, it is, if the seam angle, like
say suppose this is the vertical, the seam angle is like this, sorry, like this. No, let it be like this. Okay, if it is like this side will be turbulent and this side will be laminar, and it's at an angle to the direction of the flow. So if we'll throw like this, it will go like this, cause the ball will swing from a high pressure, this laminar side, to low pressure turbulent side. So ball will go like this. Okay, now there's the ball will move in direction of the swing. This is for in case of new ball. Now type 2. Type 2, that is reverse swing. This will happen in case of old balls. So for old balls, one side is maintained as shining side and the other side is maintained as rough side. What happens? One side, let us suppose this side is shining side. It won't like it will be always disturbed. It will be rubbed with sweat or something. It will always rub so that air to maintain the shine on this side, and the other side will remain undisturbed. As it will become more old, this side will become rougher side and this side will become smooth side. Let's suppose the left side is shining side and the right side is the smooth, right side is the rough side. Okay, so this is the ball. Let's suppose this is the rough surface and this is the smooth surface. So this is the ball, this is the vertical direction, and this is the seam of the ball as earlier. So we'll see that here, because of the rough surface, the flow will be extremely turbulent. Okay, but and here, because of the presence of seam, the flow will still be turbulent. So but here it is less turbulent, it is less turbulent as compared to this. This is less turbulent and this is more turbulent. So here the pressure is high and here the pressure is low. Okay, so thus even if the so let's suppose this, the seam is in direction of the less turbulent flow as compared to the more turbulent flow. So here high pressure, here it is low pressure. Even if the seam is in this direction, the ball should have gone towards the direction of the seam, that is this side. But as this side is high pressure and this side is low pressure, the ball will move in this direction. Okay. Thus, even though the seam is in direction of the left side, but the ball will move towards the from high to low pressure, that is in the right side. So this is called reverse swing. Now case 2, that is for medium speed. Okay, for medium speed, this is the ball, this is the seam, this is the vertical direction. For medium speed, this is the rough surface, this is my smooth surface. Just the speed will be less, so here it will be rough, laminar flow, here it will be laminar flow, here it will be turbulent flow. Okay, so this is turbulent, this is laminar. So it is low pressure, it is high pressure, it is low pressure. So what is happening now? The even the same is in this direction, because this side is laminar and this side is turbulent. So this is high pressure, this is low pressure, the ball will move in this direction only. Okay, so this is the medium speed, and case 3 is low speed. For low speed, suppose there is the ball, there is a seam of the ball, this vertical direction. Here it is rough surface, here it is smooth surface. Okay, so here turbulent flow, sorry, because the speed is so slow, there will be no effect of this itself, whatever angle you make it, no effect of seam, no effect of seam will be there.
Now, type 3 is contrast swing. In contrast swing, this is the ball, this is the seam of the ball. It will be parallel to the vertical direction. So what is happening? Again, this is rough side, this is smooth side. Rough, this is smooth. Okay. So here flow will be turbulent, here the flow is laminar. As the left side is smooth as compared to this flow is laminar here. Okay. Now the ball is like this. So ball will, as this is laminar, this side is turbulent, the ball will again move in the right direction. This is contrast swing. Okay, so when the seam effect is there, we can see when the seam effect is there, that flow can be turbulent on one side and laminar on the other, or it can be turbulent on both sides. So what will be the option? Option is A and B. This is the answer. Let us proceed to the next question. So in this question, Ks, Ka, L and Kg are thermal conductivities of aluminium, water and air. This question number 9. And at same temperature, then which of the following is true? Kg is greater than Kl greater than Ks, or Kl obviously. Solid will be having greater thermal conductivity as compared to gas as compared to liquid. So option is, so liquid as compared to gas. Option is D. Now question number 10. When the crude oil is pumped through a furnace, the heat transfer to the tubes occur when the when the hot flue gas rise and heat the tubes. Tubes are heated principally because of the process of what? Process of convection. Now question number 11. Water at 50 degrees Celsius flow over a flat plate at a speed of 1.2 meter per second, and the plate is 0.3 meter long and 2 meter wide. The boundary layer on each surface of the plane is laminar. Ensure the velocity profile is approximated by a linear expression of delta upon x is equal to 3.46 foot over Reynolds number. Determine the drag force on the plate for water. The kinematic viscosity is 1.10 to the minus 6 meter square per second and density is 1000 kg per meter. Okay, so we have to find out the velocity profile for the same. Okay, I'll give you 2 minutes to solve this question, and after that we'll go on with the solution.
Okay. So let us proceed with question number 11. So it said on a flat plate, the drag is due to skin friction acting on each side of the plate. So drag force is twice because both sides of the plate we need to calculate tau wx b dx. For linear profile, it is said the profile is linear. So u by u infinity is equal to y by delta. And tau w is equal to mu del u del y is equal to 0. Or tau w is equal to mu u infinity by delta del u by u infinity by del y by delta. And this is y is equal to 0. This is mu u infinity by delta. This is drag coefficient and this is 2 0 to L mu u infinity by delta p dx is equal to 2 0 to L mu u infinity by 3.46 root over Reynolds number by x b dx. Okay, so this is twice of 0 to L mu u infinity by 3.46 root over u infinity x by mu. This we have just put the value of delta. 1 upon x b dx. This is 2 0 to L mu infinity by 3.46 root over u infinity x by nu x square b dx. 2 0 to L mu u infinity by 3.46 u infinity by nu x b dx is equal to 2 mu u infinity by 3.46 u infinity by nu b 0 to L 1 by root x dx. 2 mu b u infinity by 3.46 u infinity by 2x to the power half 0 to L. 4 mu u infinity b by 3.46 by 4 mu u infinity b by 3.46 u infinity L by. So 4 mu u infinity b by 3.46. This is root over RE. And REL is equal to u infinity L by 1.2 into zero point 0.3. U infinity is 1.2, L is 0.3 and nu is 1.1 10 to the power minus 6. So this is 3.27 in 10 to the power 5. So REL whole to the power half is 572.08. Okay. Now FD is equal to 4 into nu into rho u infinity b 3.46 REL. This is FD, right? 4 mu जाएगा nu into rho u infinity b 146 into root over n into is equal to 4 into 1.1 into 10 to the power minus 6 into 1000 1.22 upon 3.46 into root over Reynolds number. Root over Reynolds number, we already found out that root over Reynolds number is 572.08 1.746 Newton. This is drag force. Okay, this is drag force that we needed to determine. Now we'll proceed to the next question. Consider two-dimensional laminar boundary layer flow along a flat plate. Assumed velocity profile is sinusoidal. U, capital U is equal to sine pi by 2 y by delta. Now we need to find the expression for the rate of growth of delta as a function of x. And then the displacement thickness as a function of x. And the total friction force on the plate of length L and width B. Okay. So this is question number 2. So I'll give you 4 minutes to solve this. Rather it's 7:30 already. So I'll give you 3 minutes to solve this question, and after that we'll go on with the solution. Okay. Okay. Okay, so let us proceed with the solution of this problem. Let me connect the writing pad. Okay. So this is laminar boundary layer flow. This two-dimensional and velocity profile is given, and we need to find delta by x, delta star by x, and the total friction force on the plate with length L and width. Okay. So the profile, velocity profile is given. Small u by capital U is sine pi by 2 y by delta. Okay. And u by u is equal to 1 for y greater than delta. Okay. So number 1, for flat plate u is equal to constant. So for flat plate u is equal to constant and dp dx is equal to 0, and tau w is equal to rho u square d theta by dx, where theta is equal to 0 to delta L small u by capital U 1 minus small u by capital U dy. Therefore tau w is equal to rho u square 0 to 1 small u by capital U 1 minus small u by capital U dy by dx is equal to rho u square 0 to 1 small u by capital U 1 minus small u by capital U dy by delta d delta by dx. Rho u square d delta by dx 0 to 1 small u by capital U 1 minus small u by capital U d eta. So eta is equal to y by delta. Now the assumptions are steady flow. Number 2 is incompressible flow. Okay. Now substituting small u by capital U, the equation that we have in this. So tau w is equal to rho u square d delta by dx 0 to 1 sine pi by 2 eta 1 minus sine pi by 2 eta d eta. Okay. Rho u square d delta by dx 0 to 1 sine pi by 2 eta minus sine square pi by 2 eta d eta. Okay. Rho u square d delta by dx minus cos pi by 2 eta 2 by pi minus pi by 4 eta into 2 by pi plus sine pi eta by 4 2 by pi 0 to 1. Rho u square d delta by dx 0 minus pi by 4 into 2 by pi plus 0 plus 1 into 2 by pi minus 0 plus 0. Rho u square d delta by dx into 2 by pi 1 minus pi by 4. So is equal to rho u square d delta by dx into 0.137 is equal to beta rho u square d delta by dx, where beta is equal to 0.137. Okay. Now tau w is equal to mu del u del y, that is y is equal to 0, that we already know. So if we write in terms of u by u and y by delta, that is eta, u by delta del u by u del y by delta, y is equal to 0, u by delta u by u del eta, eta is equal to 0, mu u by delta pi by 2 cos pi by 2 eta, eta is equal to 0. Tau w is equal to pi mu u by 2 delta. Now, tau we have already derived earlier. This one, rho u square into 0.137. So, this will be is equal to 0.137 rho u square d delta dx. Delta d delta is equal to 11.5 mu rho u dx. Now, integrating. Delta square by 2 is equal to 11.5 mu by rho u x plus c. Now, at x is equal to 0, delta is equal to 0. Therefore, c is equal to 0. Therefore, delta square by 2 is equal to 11.5 mu by rho u x. Therefore, delta is equal to root over 23.0 x mu by rho u. Delta by x is equal to 4.80 root over mu by rho u x. 4.80 by root over Reynolds number. Delta by x is equal to 4.80 by root over Reynolds number. So the answer is, this is the answer of A. Okay. Now the answer of B. Now the displacement thickness delta star is equal to delta into 0 to 1 minus small u by capital U d eta. So delta 0 to 1 minus sine pi by 2 eta d eta. So is equal to delta eta plus 2 by pi cos pi by 2 eta. Delta star is equal to delta 1 plus 2 by pi 0 minus 0 minus 2 by pi. Delta 1, not this one, 1 minus 2 by pi. যেহেতু delta by x is equal to 4.80 by root over Reynolds number, this we already know. Therefore, delta star by x for laminarities, laminar conflict is already said. Delta by x is equal to 4.80 by root over Reynolds number 1 minus 2 by pi. So, delta star by x is equal to 1.74 by root over Reynolds number. This is answer of B. Okay. Now, answer of C. Total friction force on one side of plate. F is equal to area of projection tau w dA. Since dA is equal to BDA for 0 to x L, then F is equal to 0 to L tau w b dx. 0 to L rho u square d theta by dx b dx. Rho u square b 0 to theta L d theta. Rho u square b theta L. Therefore, theta L is equal to 0 to L delta L small u by capital 1 minus small u by capital U dy. delta L 0 to delta L u by u 1 minus u by u dy by d delta. Delta L 0 to 1 u by u 1 minus u by u d eta. Now this we already found out to be beta. See here, if we leave this portion if we leave, this whole portion came out to 0.137 and this whole portion is only here, right? So delta L into this 0.137 beta and delta L is equal to, we know that 4.80 L by root over array L. Therefore F is equal to 137.137 4.80 L by root over RE L rho u square v. F is equal to 0.658 L u square rho b by root over RE. Okay, this is the C part. This is the answer to this question. Next we'll proceed to question number 30. Okay, let me share with you the question number 30. Air moves over a flat plate with a uniform twisting velocity 10 meter per second at a position of 15 centimeter away from the front edge of the plate. What is the boundary layer thickness? And use a parabolic profile in the boundary layer. For eta is this and density is this. Okay. So this is the last question for today's class. So I'll give you 5 more minutes to solve this, and after that we'll proceed with the solution. Okay, take 5 minutes to solve this. It is already 7:55. We'll take 10 more minutes. 5 minutes I'm giving you. 5 minutes will take for solving the last question. Okay, so start with the solution.
Okay, so we'll proceed with the solution of this last question. So it said that the profile is parabolic, and it is we have to find out the boundary layer thickness over a flat plate. Okay, so if the profile is parabolic, u by u infinity is equal to a plus by plus cy square, right? So the boundary conditions are, from here we will understand that 2 eta minus eta square how we got. So at y is equal to 0, u is equal to 0. We already know. This is flat plate. This is the boundary layer. Y is equal to 0, u is equal to 0. At y is equal to delta, u is equal to u infinity. Y is equal to delta, u is equal to u infinity. Okay. And at y is equal to delta, the shear stress is also 0 at this point. So del u by del y is equal to 0. Evaluating the constants we get for boundary condition 1. 0 is equal to a plus 0 plus 0, that is a is equal to 0. Now the apply boundary condition 2. U infinity by u infinity is equal to 1, that is b delta plus c delta square. This is equation 1. Boundary condition 2. Del u by del y is equal to 0. U infinity b plus 2 c delta is equal to 0. Or b plus 2c delta is equal to 0. And this is equation 2. So putting value of b, putting value of b from equation 2 to equation 1, we get b, we get c, right? We get c is equal to minus 1 by delta square. How? Minus 2c delta in equation 1 plus delta square is equal to c delta square is equal to 1, 0 is equal to 0. Sorry, not 0, it is equal to 1, is equal to 1. Or c minus c delta square is equal to 1, or c is equal to minus 1 by delta square. Therefore b is equal to minus 2c delta minus 2, c is minus 1 by delta square, and this is delta. So b is equal to 2 by delta, and c is equal to minus 1 by delta. Therefore u by u infinity, and a is already 0, we know. We found out a to be 0. So just put all this. U by u infinity 2y by delta minus y square by delta square. U by u infinity 2y by delta minus y by delta whole square. Now y by delta we put as eta. So u by u infinity is equal to 2 eta minus eta square. Therefore, tau w is equal to mu del u by del y at y is equal to 0 is equal to mu u infinity by delta del u by u infinity by del y by delta. Y is equal to 0. Mu u infinity by delta del u by u infinity by del eta into y is equal to 0. Sorry, this is eta. Eta is equal to 0. Mu u infinity by delta, this is 2 eta minus eta square by d eta, it is equal to 0. Mu u infinity by delta 2 minus 2 eta by, sorry, at eta is equal to 0, mu u infinity by delta 2. This is tau 2 mu u infinity by delta.
Now, applying momentum integral equation, tau w rho u infinity square d delta by dx. 0 to 1 u by u infinity 1 minus small u by u infinity d eta. Rho u infinity square d delta by dx 0 to 1 2 eta minus eta square 1 plus 2 eta plus eta square d eta. This is but we already know tau w is equal to 2 mu u infinity by delta. 2 mu u infinity by delta rho u infinity square is equal to d delta by dx. 0 to 1 2 eta minus 5 eta square plus 4 eta cube plus eta to the power 4 d eta, or 2 mu by delta rho u infinity is equal to d delta by dx. 2 eta square by 2 minus 5 eta square by 3 plus 4 eta to the power 4 by 4 plus eta to the power 5 by 5. 0 to 1. D delta by dx 1 minus 5 by 3 plus 1 by 5. This is 2 mu by delta rho u infinity 2 by 15 d delta by dx, or d delta d delta 15 mu by rho u infinity dx. So this is delta square by 2 is equal to 15 mu by rho u infinity x plus c. It is assumed that x is equal to 0, delta is equal to 0. Therefore, c is equal to 0. Therefore, delta is equal to root over 30 mu by rho u infinity x. Or delta by x is equal to root over 30 mu rho u infinity x is equal to root over 30 by root over rho u infinity x by mu is equal to 5.48 by root over Reynolds number. Now Reynolds number is equal to rho u infinity x by mu. U infinity x by nu. 10 into 0.15, 1.5 and 10 to the power minus 5. 0.2 10 to the power 5. This is Reynolds number. Therefore, delta by x is equal to 5.48 by root over Reynolds number. 5.48 by root over 1 to the power 5.0173. Therefore, delta is equal to 2.59 10 to the power minus 3 meter is equal to 0.259 centimeter. Delta is equal to 2.59 millimeter. This is the answer. Okay, so with this was the last question that we solved. With this, I am ending today's class, and will come up next week, Sunday from 3 to 5. And thank you for joining the class. I'll bid you guys bye. Have a great evening.